High wire artist Carl Wallenda, possibly the world's best-known circus performer, fell to his death today doing an outdoor stunt in Puerto Rico. For that, here's James Walker.
The only place I feel alive, said Carl Wallenda, is on the wire. And there he was this morning, 73 years old, 120 feet in the air, 10 stories above San Juan, performing as he had for 58 years. The idea was to promote a circus act he was performing with his granddaughter. So, a high wire walk across the street from one beachfront hotel to another. But as he reached halfway, the ocean wind suddenly picked up, gusting to 30 knots. And Carl Wallenda, the best man in the world on a high wire, fought for his balance. "200 people saw Wallenda fall. Many rushed to help, but it was too late. Wallenda's body had struck a parked taxi. He was dead on arrival at the hospital." Carl Wallenda and his family came to the United States from Germany in 1936, brought here by John Ringling and the Ringling Brothers and Mardeman Daly Circus, which was their home for the next 18 years. It was a family act, but Father Carl was the star. Frequently, he appeared alone, like in this stunt when he walked across an 1,100-foot cable strung 700 feet above the Tallulah Gorge in Georgia. He was so supremely confident that he did it wearing a microphone to narrate his own crossing.
It's a little windy now. More wind than I expected. God is with me. I believe everything will be all right.
Carl Wallenda is the fifth member of the family to die while walking the high wire, the latest in a series of tragedies that began in 1962 with the seven-man pyramid, developed and perfected by Father Carl. During a Detroit appearance, the pyramid collapsed. 2 family members fell 40 feet to their death. Carl's son Mario was permanently paralyzed. And Carl Wallenda did not escape untouched. He suffered a broken pelvis and a double hernia, but he always returned to the ring and his high wire. This afternoon, Carl Wallenda said that despite his uncle's death, the act will go on. James Walker, ABC News.
His final performance. At 73, a high wire walk 10 stories up to promote a circus appearance with his granddaughter. The patriarch of the great Wallendas was best known for the creation of their 3-level human pyramid. It was also their most dangerous act. This happened in practice. In 1962, the pyramid collapsed for real. 2 were killed and an adopted son crippled for life. Despite it all, Wallenda told interviewers he was not afraid.
Well, even in a big fall when I lost 2 people, they got killed, and my son is paralyzed for life. And I never failed. And 24 hours later, I was up on a wire with a broken pelvis bone.
The Winnebago County Board.
All right, so the only question that I have regarding that is, all right, this was weird. It's keep me out.
High wire artist Carl Wallenda, possible
One across the street from one beach
What's the purpose of the pole that these people are carrying?
hotel to another.
What's the purpose of the pole? You know the answer, right? The answer is because it helps them balance themselves. So the question is how. In this case, it's because it's too windy, it's having a hard time balancing himself. But the pole serves a definite purpose. The purpose is so that you can balance yourself better. So how does that help you balance yourself better? So that's what we're. So we've seen this before. Notice that they just pull them out to 12 Gs. When it was going up to 12 Gs, okay, so there's 2 types of accelerations. One of them is the centripetal acceleration, because he's got speed, but also he's still rotationally accelerating as well. So you got rotational acceleration as well as you got the centripetal acceleration. Now, if you got rotational acceleration as well as the centripetal acceleration, this 12 Gs, what did that represent? The answer to that question is obviously it's got to be representing the total acceleration, right? So how do you get the total acceleration out of a situation where you have 2 different accelerations? There's one acceleration which is directed towards the center, and there's a second acceleration which is directed in the direction of the rotation, on the direction of the rotation. So how do we figure out the total acceleration if that's the case? Galileo's Incline Experiment. The purpose of the Incline Experiment was that it was trying to measure the acceleration due to gravity, and there was an underlying assumption in that experiment that we will question. All right, so this is going to be from the internet, so let's just wait for a second before it takes your hand.
Galileo had spent half a lifetime trying to prove the Earth moves. Now, he would come to terms with something much more basic, the mathematics of motion itself. But motion is hard to measure.
It all happens just a bit too fast for you to see what is going on. Galileo hit on this wonderful idea of slowing down the motion. So instead of trying to watch a thing falling, he rolled balls down very gentle slopes so that the speed built up very, very slowly.
Galileo reasoned that as balls rolled down slopes, they would accelerate, just as they did in freefall, but more slowly. As a young man, Galileo had designed a very accurate inclined plane, one of the most important pieces of experimental apparatus in the history of science. Galileo left behind no plans for his inclined plane, but based on his experimental notes, Professor Roberto Caparelli is using what he believes to be Galileo's original design to discover how he was able to accurately measure acceleration.
Galileo studied the inclined plane, slowing the motion of falling bodies until he was able to observe the phenomena. He was able to measure exactly how fast a ball would roll, timed with the swing of a pendulum. Galileo was sure that the steady acceleration must be governed by a mathematical rule.
So he takes this very gentle inclined plane and he lets the ball roll down and he watches how that ball speeds up and he measures how far it goes in a certain time. And then he makes his first empirical discovery that if in the first unit of time it goes 1 unit of distance, in the next unit of time it travels 3 units of distance, and in the next 5, and in the next 7. So it has this beautiful numerical progression, 1, 3, 5, 7. And he calls this the odd numbers rule. And he really is entranced by this. He knows he's made a huge discovery.
Galileo had found a mathematical rule for accurately predicting the motion of objects in the real world, a universal law which applied to any falling bodies.
Underneath this beautiful empirical law that he found a deeper law, clearly a deeper law, using mathematical logic and deductions. And this was actually the key to all the later great successes, first of Newton and then of Einstein and all the other wonders of modern science.
As a young man, Galileo had revolutionized astronomy. But at the age of 74, his last great book revolutionized the physics of motion.
From the point of view of physics, his most important contribution is his discourse on the two new sciences. Indeed, it's that book that provides the real foundation for Isaac Newton.
All right, so the purpose of the incline experiment is to slow the motion down, right? So that he can measure the distances in every single consecutive time interval. Only to realize that the distance is getting increased. This was actually our first lab that we did in class. So this was our first lab that we did. We did the incline experiment, sir. And then we found out that, yeah, the rolling objects will accelerate. Okay, so we know that all falling objects will accelerate at the same rate. The question is, will all rolling objects will accelerate at the same rate as well? All right, so which means that this block that you're looking at, cylinder, and this rim, do you think they will roll at the same rate and reach the bottom at the same time? All right, so we know that they will fall at the same rate, but will they roll at the same rate? If they roll at the same rate, then you're fine. You should be able to come up with the right acceleration. But what if they don't roll at the same rate? Then what? Where do you go from there? All right, so the falling chimneys, most of the time, not all the time, will break at something. Okay, they will break somewhere in the middle. All right, so the question is why? Seems like it's not a very interesting question, but it is, as you will find out. There's a backstory that's going to make it interesting, but for now, let's take a look at it as a physics discussion topic. All right, so rotational motion is what we are covering. All right, so this thing is going to be rotating in this direction. All right, so this is the angle that it's going to spun out. All right, the term that I want to emphasize is the angular displacement. The angular displacement just means angle. When you look at the setup, the angle is going to be expressed in terms of radians. 2 pi radians is going to be 360 degrees. And so 2 pi radians is going to be one single revolution. So 1 revolution is 2 pi radians, which is 360 degrees. So that's the only thing you need to know. This is known, theta is known as the angular displacement. So we will get to look at the angle or the angular displacement in terms of radians. Proper units is going to be radians, not degrees. It's going to be radians. Okay, so as long as you make that connection in your head, I think you were perfectly. So pick out the best answer and place it in the chat. All right, very good. Radiant speed. Give yourself 5.4. The next term that we will get to use is the angular velocity. Angular velocity is how fast the angular displacement changes in time. So you're at this angle and now you're at a different angle, right? So there's going to be an angular displacement in this direction. So how fast the angular displacement changes in time is your angular velocity. Okay, so the terms that you're looking at, these are the Greek letters. Theta is a Greek letter. It looks like W, but that's omega. Omega is a Greek letter. So how fast the measured angular velocity, how fast the measured angular displacement changes in time is your angular velocity in this case, which is going to be expressed in terms of radians per second. It's going to be expressed in terms of radians per second. So that's our angular velocity. So that's the answer. All right, so the best answer in this case is going to be radians per second. All right, so the next term is the angular acceleration. This is how fast the angular velocity is changing in time. So here's your initial angular velocity, here's your final angular velocity. So your angular velocity is changing in that direction, which means that you're accelerating in this direction. So alpha represents angular acceleration, omega represents angular velocity, and t is your time. All right, so angular acceleration, angular velocity, or speeds, or rotational speeds, they mean the same thing. So the angular acceleration is going to be expressed in terms of radians per second squared. All right, so we got the best answer. Angular acceleration. 9.4 minutes ago. Which one is interesting? I think this is. All right, so the best answer in this case, radians per second squared. All right, so let's focus on the mathematics at this one. All right, mathematically, this stuff is real easy. I mean, compared to the stuff that we've been doing recently, this is a welcome change. Mathematically, this stuff is easy. The only problem that we will have is the convergence. So we'll have to focus on the convergence on this one. Case in point. So we got a blade. The blades in a blender will be, they rotate at a rate of 6,500 RPM. So revolutions per minute, 6,500, right? So you turn off the motor, and it's going to slow down to stop within 3 seconds. So it's going to go from 6,500 RPM to 0 within 3 seconds. So what's the angular acceleration, right? All right, so that's what we're going to be focusing on. Okay, so RPMs. So initially, it's 6,500 RPMs, revolutions per minute. So it's going to go from 6,500 to 0 within 3 seconds. So boom, 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 what's the acceleration? That's that. All right. So the only thing we have to do is just remember the proper units, radians per second. So RPM needs to be converted to radians per second. 1 revolution is going to be 2 pi radians. 1 minute is going to be 60 seconds. And then you do the conversion, so it's going to give you the radians per second. Okay, I made it look real easy, but there's something that you will have to remember. Every time you see pi, you have to use 3.14. Okay, so pi is a number, so you will have to use the numeric form of pi for this to work out. All right, so you got your initial rotational speed, you got your final rotational speed. So what's the acceleration if that's the case? All right, so how fast the rotational velocity changes in time is going to be your acceleration. So the final rotational speed is 0. All right, no, the numbers, plug the numbers in and you're done. So we end up getting the rotational acceleration in terms of radians per second squared. Okay, so what else do we have? Okay, so now we got the angular versus the tangential variables. Okay, so here's your angular displacement. Okay, can you figure out the length of the curvature if you know the angular displacement? The answer to that question is yes. So if you want to figure out the length of the curvature, which is known as the arc length, one thing you need to know is this angle and the distance to that point where you're interested in the curvature, right? All right, so that's pretty much it. So if you know the angle, which is that's the angular displacement, if you multiply by the radial length or the radius that you got, then you can figure out the length of this curvature, which is known as the arc length. All right, so which means that it's going to give you the distance along the direction of the curvature. If you know the angular displacement, and then you can multiply it by r, so the r is going to locate where the curvature is located. This is where the curvature is. All right, likewise, if you know the angular velocity, which is this, can you figure out the speed of this object along the direction of the curvature, which is known as the tangential speed? Tangent means it's a vector or a line touching the curve, but not crossing it. That's what it means. Now, from here, you can figure out the tangential speed. All right, so you know the angular speed at this radial distance. You can figure out the tangential speed, the speed along the direction of the curve. So angular term times r is going to give you the tangential term. So the motion along the curvature can be figured out. All right, so this one is your angular acceleration. Can you figure out the acceleration along the direction of the curve, along the direction of the curve? The answer to that question is yes. If you know the angular acceleration, along the direction of the curve at a radial distance r from the center is going to give you the tangential acceleration. Okay, so the only thing you need to remember, literally, your angular terms are on the far right. If you multiply the angular term with the radial distance, in this case the radius, it's always going to give you the expressions along the direction of the curvature. Here's the length of the curvature. Is the speed along the direction of the curvature? Here's the acceleration along the direction of the curvature. Linear speed along the direction of the curvature. Linear acceleration along the direction of curvature. Linear length along the direction of curvature. That's it. So the linear terms will be expressed in terms of meters and seconds. All right. Okay, so figure out the best answer. Figure out the best answer. Okay, so what do we have here? What do we have? So we have a boy and a girl. They're riding on a merry-go-round, which is turning at a constant rate. So angular speed or acceleration, whatever, is going to be constant. All right, so which one has a greater angular displacement? So which one is going to be at a greater angle? Both of them will be at the same angle, guys. Both of them will be at the same angle. All right, so the angular displacement is going to be the same. So C is just the same. C is the best answer. All right, so now we're looking at the fastest linear speed on a merry-go-round. And the fastest linear speed is going to be at the greater radial distance. So which means that the one near the outside, right? So B is the best answer for this one. So B is the best answer. Okay, so which one is going to have a greater angular speed? Angular speed is going to be the same for both of them, right? So C is the best answer. So you guys are finally catching up. So the answers are looking pretty good. You guys are catching on. All right, so we got a rigid body rotating. So we got a rotating rigid body. Which of the following is an accurate statement? The center of rotation is the center of gravity. We don't care about that. All points on the body are moving with the same angular velocity. That's correct, actually. All points on the body are moving with the same linear velocity. That's not correct. Linear velocity depends on the radial distance. The center of rotation is at rest, i.e. not moving. That may be correct, but that's not what we're looking for. So B is the best answer. B is the best answer for that one. Okay, so we got a bicycle. They give us the diameter of the tire. It's going to travel for 8 kilometers. So 8 kilometers is almost 5.5 miles, about 5 miles. All right, so how many revolutions will the wheels make? That's what we're going to look at. This one is a cute exercise. So diameter is twice the radius. It's going to be 68 centimeters, expressed in terms of meters. Only thing I have to do is just move the decimal to the left by 2 decimal places. All right, so our radius is going to be out the diameter. So we got that number. S is going to represent the total linear length that the tires will travel. All right, so that's the total arc length. All right, so it's going to be 8 kilometers, so it's going to be 8,000 meters, roughly about 5 miles. So how many revolutions does it make? So theta is what we're interested in, and we want to express it in terms of revolutions. Expect a few questions like this on the multiple choice second of the test. So this is where we go. All right. So solve for theta. And it's going to give us, in terms of radians, convert it to revolutions. It's going to take about 4,000 revolutions. Cool. All right, so. Coming down. All right, so there's not only a centripetal acceleration involved here, but also there is a rotational acceleration. So it's a combination of both. All right, so if you get a combination of both accelerations, how do we figure out the total acceleration? So that's the question that we're trying to answer here. So you got a centripetal acceleration because it's got tangential speed here, right? So it's got speed along the direction of the curvature, which is going to be responsible for the centripetal acceleration. And so the centripetal acceleration can be expressed in terms of the rotational speed. All right, so you got the tangential speed expressed in terms of rotational speed. So here's the generic centripetal force formula. So centripetal acceleration formula. So we'll do a back substitution right there. All right, and get rid of the like terms. All right, so centripetal acceleration can be expressed using the tangential speed as well as the rotational speed. All right, so, okay, so there's nothing new here. Let's move on to the next portion. What if there's rotational acceleration as well? All right, so not only do we have centripetal acceleration, what if we also have rotational acceleration? So due to the rotational acceleration, we will get the tangential acceleration. So rotational acceleration is going to give you the tangential acceleration. All right, tangential acceleration, tangential acceleration, and the centripetal acceleration. So if that's the case, how do you find the total acceleration of this system? Okay, so the way to do this sort of stuff is, remember, you're dealing with vectors. As long as you're not changing the size and the direction of these vectors, you can move these vectors any way you want. So what I'm going to do is I'm going to take the tangential acceleration, move it to the left in order to make a small triangle. All right, so here's the centripetal acceleration. Here's the tangential acceleration. So I'm moving the tangential acceleration to the left in order to make a triangle. And that's exactly what I did. All right, so here's the base, here's the height. All right, and then I'll apply the Pythagorean theorem. So I'll take the base, square it. I'll take the height, square it, and sum them up. Take the square root, and this is going to give me the total acceleration. not only will I get the total acceleration out of this, but also I can figure out the direction of this total acceleration. All right, this total acceleration is not going to point towards the center. It's going to be coming at an angle relative to the center. So if you know the height, if you know the base, you can figure out the angle by using the tangent of the angle. By taking the inverse of the inverse tangents of both sides, you can figure out what that angle is. And that's exactly what we'll do. So we'll use, you guys are taking college physics, so we will use Schrödinger in order to solve this problem. So that's how the problem is solved. Rotating merry-go-round. So it's going to make one single revolution. It takes about 4 seconds for it to do so. So what's the linear speed, which I'll see at about 1.2 meters from the center? And what's her acceleration? So we got one single revolution. So it's going to take 4 seconds. The person is seated at this radial distance away from the center. So we want the linear speed, so that's the tangential speed. And we also want the acceleration for that. So it's a single revolution. So that's your angular displacement. This happens in 4 seconds. So linear speed is the tangential speed. And we also want the linear speed at this distance. We also want this acceleration at that point. All right, so if it's got acceleration at that point, if it's moving at a linear, if it's moving at constant speed, then there's only going to be a centripetal acceleration. All right, so we got this rotational motion. All right, so what is it that we want? We want the tangential speed. Here's the tangential speed formula. All right, so for us to be able to use this formula, we need to know what omega is. Omega is the rotational speed. So rotational speed is angular displacement over time. So this is the angular displacement. It's going to be the angular displacement over time. So we know what the angular displacement is going to be in this case. So we do a back substitution. All right, so angular displacement is going to be 1 revolution within 4 seconds. So this 1 revolution needs to be expressed in terms of pi radians. So it's going to be 2 pi radians. And instead of using pi, we end up using 3.14. All right, so you have to, every time you see pi in these computations, you have to use the numeric form of pi, which is an approximation of 3.14. That's what you need to use, divided by 4 seconds. All right, so that's going to give us the tangential speed. Happens to be about 4 miles per hour. All right, let's focus on a second example problem. So we got this wheel. We know its diameter, and it's accelerating from 130 RPMs to 280 RPMs in 2 seconds. So it goes from 130 to 280 RPMs in 2 seconds. So figure out the angular acceleration and then the radial and tangential components of the linear acceleration. So figure out the angular acceleration and then figure out the radial and the tangential components. Radial component is the same as the centripetal component. So that's the component which is directed towards the center. And then we are trying to figure these out at the edge of the wheel 2 seconds later, 2 seconds into the motion. So it's going to, within 2 seconds, it's going to go from 130 to 200 RPMs. And then, so figure out this total acceleration, which means that we need to figure out the radial and the tangential accelerations before we figure out the total acceleration. This is multiple choice quality. All right, so let's write out what we already know. So we know the diameter, it's twice the radius. So radius is going to be half that number. Its initial rotation is at 130 RPMs, revolutions per minute. The final is going to be 280 revolutions per minute. So it's going to take for 2 seconds to go from this speed to that speed. All right, so I'm doing the conversions from revolutions per minute to radians per second for both of them. All right, so the convergence, this is, you have to practice this sort of stuff or else you will get really confused during the test. You have to practice the convergence for this. All right, because in life, we talk about RPMs. In physics, we talk about radians per second. So you should be able to get real comfortable doing the conversions back and forth, or else your numbers will never make sense. All right, so let's figure out the angular acceleration, tangential acceleration, and from that, we'll figure out the total acceleration. All right, this is 2 seconds later. All right, so we'll come up with the rotational acceleration. Rotational acceleration is going to be expressed in terms of tangential acceleration. And then we'll figure out the centripetal acceleration 2 seconds later, and from that, we'll find the total acceleration. All right, so the rotational acceleration is how fast the angular velocity changes in time, or rotational velocity changes in time. And so we got the initial, we got the final. For the initial, we use this. For the final, we use that. All right, so we got our number in terms of radians per second squared. All right, now we want to know what the tangential acceleration is. The centripetal acceleration is 2 seconds later. Tangential acceleration, we'll use this formula for that one. Obviously, if you know the rotational acceleration multiplied by r, it's going to give you the tangential acceleration at that point in terms of meters per second squared. Now the centripetal acceleration, obviously you got two formulas. You can use either. All right, so we can either use this one or we can use that one. All right, we know what the rotational speed is 2 seconds later, so let's use that one. That's easier. All right, so this is our centripetal acceleration. So if you know the tangential and the centripetal accelerations, now what you need to do is a vector addition to get the total acceleration 2 seconds later. So it's going to be the hypotenuse of the right angle triangle that you create. All right, and so that's it. So this is the formula, plug the numbers in, and then it gives us an acceleration in terms of meters per second squared. All right, it's slightly larger than the centripetal acceleration as it so happens. And it's going to be pointing to the side just a little bit relative to, it's going to be pointing to the side just a little bit relative to the direction of the centripetal acceleration. All right, for whatever the reason, I decided I didn't care much for calculating the angle there. All right, so constant acceleration makes motion predictable, obviously. All right. So if you know the time, you know the location, provided that the acceleration is constant. If you know the time, you know the speed at that time, provided that the acceleration is constant. Also, if you know the location, you know the speed at that location if you make the acceleration constant. So that's what it is. So as this all happens, you can do the same with rotational motion. So the only thing you have to do is you have to transform your symbols to the rotational symbols. Displacement becomes angular displacement. Initial speed becomes initial angular speed. Final speed becomes the final angular speed. Acceleration becomes the rotational acceleration. So x is going to become theta. Speed becomes omega. Initial speed becomes omega naught, and then acceleration becomes alpha. All right, so these equations will get transformed into their rotational counterparts. So this formula becomes that formula. This formula becomes that formula, and so that's it. So these equations are going to be used precisely in the same manner that we used to use the linear kinematics equations. Case in point, here's an exercise. All right, so we got a car engine, the automobile engine, slowing down from 45 RPMs to 1200 RPMs in 2.5 seconds. So it's going to take 2.5 seconds for the engine to go from 4,500 RPMs to 1200. Assuming that the acceleration is constant, let's figure out the angular acceleration and then figure out the total number of revolutions it's going to make. All right, so that's what we have to do. I think I just sketched it out. All right, so here's the initial angular velocity, revolutions per minute. The final, in terms of revolutions per minute, it takes 2.5 seconds. So what's the angular acceleration in terms of radians per second squared? And what's the total number of revolutions? So you have to express this in terms of radians and then convert it to revolutions. All right, so we'll have to do the conversion. 2 pi is going to be 1 revolution. 1 minute is going to be 60 seconds. And don't forget that every time you see pi, you have to use 3.14. So it'll give us the everything in terms of radians per second. I'm talking about the speeds. All right, so these are the symbols available. Based upon those symbols, it makes sense to use this formula. So isolate alpha from here, so just get rid of omega naught. All right, so the algebra is algebra, just follow the rules. That's what I'm doing. So this is going to give us the acceleration, right? Acceleration is how fast the velocity changes in time. Angular velocity changes in time. So we got our acceleration. So, and then the numbers in terms of radians per second divided by time, which is in terms of seconds. So we end up getting an acceleration in terms of radians per second squared. All right, so now let's figure out the the number of revolutions it takes for it to go from this to that. All right, so you got two formulas. That's got theta, the first one and the last one. All right, so either one is going to work. The first one is easier, so that's what I'm going to pick. So I'm just going to pick the first one. I'm picking the first one. So I think the only thing we have to do now is just plug the numbers in. That's it. Because I don't see any zeros, just plug the numbers in. This is a negative acceleration, which means that it's slowing down. So it's going to take this amount of angular displacement in terms of radians, convert it to revolutions. So it's going to take about 120 revolutions to go from that initial speed to that point.
3, 2, 1, mark.
Have on the human brain.
That's it. You're going to have to really strain.
Pennsylvania.
All right, so it's a centrifuge. Obviously, they are just going to speed it up. When it's speeding up, it's got two types of accelerations. You got a centripetal acceleration, and then it's got obviously rotational acceleration. That's going to give you tangential acceleration. So the G meter actually reads the total acceleration. All right, so this is another exercise. All right, so a couple of things we know about the centrifuge. You know that it's going to take 1 minute for it to undergo 20 complete revolutions. So it takes 1 minute for 20 revolutions. So a couple of things that we can figure out. So what's the angular acceleration? Assume constant. And its final angular speeds in terms of RPMs. All right, so it's going to take 1 minute to go through 20 revolutions. So figure out the angular acceleration and figure out the final angular speed at the end of that 20 revolutions that we got. So we got 20 revolutions in 1 minute. Figure out the acceleration, assume constant, and then figure out the speed, angular speed, at the end of this 20 revolution sequence, and express it in terms of revolutions per minute, not in terms of. All right, so it's going to be expressed in terms of RPM. So the revolution needs to be expressed in terms of radians. And once again, pi is going to be 3.14. All right, so these are what's given. Based upon that, it makes sense to pick the first formula. Initial angular speed is going to be 0. All right, so this term is going to drop out. That term just dropped out. So solve for alpha. I'm just going to rewrite both sides. All right, so get rid of 2, and then get rid of t squared. All right, so here's the final expression for acceleration. All right, so 1 minute is going to be 60 seconds. All right, so and then we plug the numbers in. All right, so we got the acceleration, constant acceleration in terms of radians per second squared. All right, so the next step is let's figure out the speed at that point. All right, so rotational speed at that point, you can find it from here or you can find it from there. It doesn't matter. Pick and choose. This one is easier. So I'm just going to write out the equation. Initial speed is 0, so that just goes away. And that's it. So here's the final equation. Plug the numbers in. We already figured this out. And then you get the number in terms of radians per second, and then convert it to revolutions per minute. So it takes 40 RPMs for it to get. It takes 40 RPMs for it to get up to that speed. So it takes 40 RPMs for it to turn 20 revolutions within 1 single minute. All right, problem number 7, I'm not interested, so I'm just going to move forward. These are simple exercises. And these questions are multiple choice quality. Okay, so rotational motion. All right, so displacement is the shortest distance between 2 points, is the final location indicated as an arrow. So it's a vector. Rotational displacement is the angle. Proper units is going to be radians. Average speed is the measured distance over measured time. Rotational speed is the measured displacement, angular displacement over time. Proper unit for rotational speed is going to be radians per second. Average acceleration is how fast the measured velocity changes in time. Average rotational acceleration is how fast the measured angular velocity changes in time. Arc length is the length of a curvature. You can figure out the arc length if you know the angular displacement. So the only thing you have to do is just multiply the angular displacement by the radial distance. Tangential speed is the speed along the direction of the curvature. You can figure out the tangential speed if you know the rotational speed. So if multiplying the rotational speed by the radial distance, it's going to give you the tangential speed at that radial distance. Speedometers are configured to read only the rotational speed, how fast the angular displacement changes in time. That's it. The linear speed of the car is going to depend on the radius of the wheels. So if you have larger wheels, the car is going to be moving faster than what's indicated on the speedometer. So speedometer value is going to remain the same. The car is going to move faster than what's on the speedometer. So the speedometer is configured to read only the rotational speed. The linear speed of the car depends on the radius of the tires, the radius of the wheels that you're looking at. So the cars with larger wheels will be moving faster than what's indicated on the speedometer. So that's what it means. Tangential acceleration is the acceleration along the direction of the curve. You can find the tangential acceleration if you know the rotational acceleration. So by multiplying the rotational acceleration with this radial distance, you can figure out the tangential acceleration at that distance. All right, so if an object has both centripetal and rotational acceleration, how does one calculate the total acceleration? All right, so you do a vector addition, which means that you create a small triangle. One acceleration becomes the base, the other acceleration becomes the height. So the only thing you have to do is just calculate or compute the hypotenuse of this triangle. The hypotenuse is that triangle is going to give you the total acceleration. All right, so 12 G's during a rapid onset that a pilot is exposed to is the total acceleration that we just discussed. All right, so the linear motion becomes predictable by fixing the acceleration. Rotational motion also becomes predictable by fixing the acceleration to a constant value. Inertia is the tendency to retain initial motion or resistance to change in motion. What causes inertia is mass. Moment of inertia is the rotational inertia, something that we will discuss shortly, whatever that means. And potential energy is the stored energy. If it's gravitational, it's related to height. If it's elastic, it's going to depend on how much something is stretched or compressed. Kinetic energy is the energy of motion for a given mass, depends on the speed. Mechanical energy is a combination of kinetic and potential energies. Conservation of mechanical energy is the constancy of mechanical energy. All right, so these are the topics that we already know. Anything else that we skip are the ones that we will fill in later, more like shortly. All right, second law. Force is what causes acceleration, right? So the force acting on this mass is going to cause it to accelerate. Except in this case, the mass is rigidly attached to this point. All right, so which means that this force is going to cause rotational motion. As a result, this force is going to become a rotational force. All right, so this rotational force is known as torque. We end up using the Greek letter tau for that one. This is Greek, all right? It looks like T. It's the Greek letter T. It's known as tau. So this represents torque. Torque is a rotational force. So you can figure out the torque if you know the tangential force and the radial distance of this force relative to the point of rotation that you're looking at. All right, so it's going to be a combination of both of them. So that's your torque that you got. All right, so I'm just going to rewrite that. So it's going to be force times the radius or radial arm, or this is known as the lever arm in physics. If the force is coming in an angle, just like that, relative to the radial direction. So it's coming in an angle relative to radial direction. The component of the force which is going to be responsible for torque is going to be the tangential component. Tangential meaning that's going to be tangential to the curvature that is going to draw out, right? Because it's going to trace out a circle here. So this force is going to have two components. One is the parallel component. The parallel component is parallel to the radial direction. And the second one is the tangential component. The tangential component is the vertical component that you're looking at. All right, so once again, you make a small triangle. This is the base, this is the height of the triangle. So this tangential component is going to be related to the height. All right, so the tangential component is related to the height. All right, so if you know the angle, obviously this height, the tangential component is going to be the sine of the angle of this force that you're looking at. So, which means that we can take this term, substitute into that term. So that's going to give us the complete expression for the torque that you're looking at. All right, so the tangential force is going to cause a tangential acceleration. All right, so I'll do a tangential acceleration can be expressed in terms of its rotational component. All right, so I'm going to take this expression and then substitute back into that formula. Then I'm going to clean this up. So you got R and then R. R and R is going to give you R squared. Then we came up with an expression for torque. And then what I'm going to do is I'm going to compare this rotational torque expression to the linear force expression. All right, so I'm going to compare these two formulas to each other. So force becomes rotational force, the acceleration becomes rotational acceleration, and the mass becomes some rotation mass-like term. So this is known as rotational inertia. All right, so it's a rotational mass, it's rotational inertia or moment of inertia. That's what it means. All right, so moment of inertia is the same as rotational inertia. It's a rotational mass-like term. There's not only mass, but also there's some kind of a radial distance involved. All right, so this is your moment of inertia or the rotational inertia or rotational mass-like term that we will be focusing on. All right, so and then when you do a back substitution, when you substitute this expression into this formula, it's going to give us the final formula for torque. So the final formula is going to look like, you got this rotational mass-like term, the rotational inertia times rotational acceleration. All right, so force acting on the mass is going to cause it to accelerate. Rotational force acting on the rotational inertia is going to cause it to accelerate rotationally. So these two expressions are identical. So you get the linear expression. You also have the rotational expression for the same linear expression in essence. All right, so the torque is going to be expressed in terms of newtons meter. All right, and that's it. Literally, the only thing that I'm interested in out of this discussion, just for now, is the rotational mass, rotational inertia, or moment of inertia. Technical term is moment of inertia. It's a rotational mass-like term. That's what I like to use, or it's known as rotational inertia. All right, so rotational mass-like term is more like it because it also has this radial component. All right, so if you got multiple masses, you will have to sum up the inertia of these multiple masses. Okay, let's skip that one. That's not what I'm looking for now. I'm gonna go back to these definitions once the concepts are set in your mind. So those discussions are a little bit too abstract right now. All right, so we got the tightrope walkers. They have a pole. So the purpose of the pole, you know the purpose of the pole, so that they balance themselves. Okay, so a couple of things about the poles, which will matter. All right, so the length is going to help, as well as its mass is going to help. So you want something which is relatively heavy, and you want something which is relatively long. All right, so how does that help? All right, so the moment of inertia, or rotational inertia, or rotational mass-like term, represents tendency to retain rotational motion, initial rotational motion, or resistance to change in rotational motion. All right, so let's focus on the resistance to change in rotational motion. Now, longer the pole is, the bigger its moment of inertia is going to be, rotational inertia is going to be, and more it's going to resist change in rotational motion, and that's what you want. All right, if you're a tightrope walker, you want something which is going to have an extremely large rotational inertia, extremely large moment of inertia, and that's what you want. So you want something which is relatively massive. You want something that's massive enough. It's going to be heavy enough, but just so that you can carry it. But at the same time, it needs to be extremely long, so it offers a lot of resistance to rotational motion. So if you're about to lose your balance, you can just lean into it. So that's what you need to do, because it's going to resist your attempt to rotate it. That's what it means. So this is the formula that we will use for. So you're holding it in the middle. The more massive it is, the larger the rotational inertia is. So more resistance is going to offer to your attempt to change its motion. And the longer it is, likewise, more resistance is going to offer to your attempt to change its motion. As a result, you're going to be able to balance yourself out. All right, so that's the purpose of it. How well does it work? Well, it works incredibly well. All right, that's the reason why you don't see a lot of tightrope walking accidents. All right, so Nick Wallenda is the grandson of the guy who ended up dying in 1970s. Remember the guy who was trying to cross, and then eventually it was too windy, and then he was not able to balance himself. He fell to his death. All right, this is his grand.
Let's do this, baby.
Thousands of people packed the streets below to see Nick Wallenda complete the walks 50 stories up in the air.
I don't know, this happened maybe roughly about 10 years ago, I think, live on TV in Chicago, here in Chicago.
His father was in radio contact, occasionally offering some unhelpful advice.
Nick, if you get a chance, give it a bounce one time so I can watch the reaction.
It's moving, Dad. I'm not going to give it a bounce.
All right.
This first walk, on a 70-foot incline, was broadcast with a 10-second delay in case anything went wrong. It took him under 7 minutes to make it across.
There we go. First down.
All right, so the first one was a test run. He just wanted to make sure that everything was working fine. The second one, he did blindfolded, which means that as long as you got the right pole, all right, you can just lean into it to balance yourself. You don't need to see what's going on. And that he was able to actually cross the same length blindfolded.
I think you probably saw me shaking like a leaf. That wire was shaking underneath me, and I just wanted to make it to the other side. I wasn't going to think twice. I was getting on the wire. I'm going. So I need everybody to be nice and quiet for me, okay?
Shortly after, he did the whole thing again, blindfolded, and this time in just over a minute.
Took him, first one took him more than 4 minutes. Second one took him under a minute.
The crossing saw him set 2 world records.
Love you guys.
All right, so different geometries will offer different amounts of rotational inertia or moment of inertia. A couple of geometries that we will be interested in. One of them is the thin hoop. This is the one that we will focus on. All right, I mean, if you have like bicycle tire, this is the thing to use. All right, so notice that the mass is going to matter. Notice that the radial distance to the point of rotation is going to matter because you have to square that. Second one is a solid cylinder. All right, so you got the thin hoop, and then you got the solid cylinder. So notice that solid cylinder is going to have a moment of inertia. It's going to be half the rotational inertia of the thin hoop that you got. The third one that we're going to be interested in is this uniform sphere. All right, once again, all of them mr squared, and then it's always going to be some kind of a fraction of this mr squared. So everything's going to get multiplied by a number. So if you multiply mr squared by 2/5, it's going to give you the moment of inertia, rotational inertia of the uniform sphere. If you multiply by 1/2, it's going to be the solid cylinder. If it's multiplied by 1, it's going to be thin hoop. And also another thing that we will be interested in is once again this long rod that you're looking at. But this time we're going to be interested in what happens if it's the point of rotation is placed at the base of it. So this time it's ml squared. L is once again the radial distance, so it's the same as r, except everything is going to get multiplied by 1/3 in this case. If you're holding it in the middle, it's going to be 1/12. If you're interested in rotation relative to one end, it's going to be 1/3. So those are the main ones that we have to look up in the future. All right, so both these cylinders have the same mass. So masses are the same, but they're not, which means that they will have the same amount of inertia, but they're not going to have the same amount of rotational inertia. All right, the rotational inertia also depends on the radial size. All right, so this has a much bigger radius, so the mass is distributed onto a much larger surface area. As a result, this one is going to have a much larger rotational inertia, which means that it's going to have a larger tendency to retain that initial rotational speed, or it's going to offer a lot more resistance to changing that rotational motion. All right, so larger the radius, the bigger the moment of inertia for a given mass. All right, so this is a bit of a mathematical exercise so that you guys know how to pick the right formulas for the different geometries. All right, so we got a sphere. We know the mass, we know the radius. And so the axis of rotation is going to be at its center. So determine its moment of inertia. All right, so if it's a sphere, obviously, we got the mass, we know the radius. The only thing you have to do is just pick the right formula. So here's the expression that we have to pick. Uniform sphere. It's going to be 2/5 mr squared. And then just plug the numbers in. And that's pretty much it. All right, so that's how you do it. All right, now the bicycle wheel. So let's play the same game using a bicycle wheel. So this time the diameter is given, and so the total mass is given. And the mass of the hub can be ignored. Why? Because it's right at the center of rotation, so it doesn't have any radial displacement. Anyway, so here's the moment of inertia is what we're looking for. This diameter, I said, screw that. Let's call it a radius because I don't want to do one extra computation on this thing. All right, so expressed in terms of meters. So the mass is given. All right, so if it's a bicycle tire, you can use the moment of inertia for the hoop. So it's going to be mr squared, and then you plug the numbers in. And that's it. So that was straightforward. All right, so the kinetic energy, the rotational kinetic energy. All right, so got the linear kinetic energy. of something which is rotating, for example. It could be a wheel, it could be a ball, or whatever. All right, so let's figure out its tangential. So that this would be the tangential speed of this, whatever's rolling. You're looking at the tangential speed of this thing. So tangential speed can be expressed in terms of rotational speed. And so you square the expressions within the parentheses, and then you end up getting this mr squared term. So this is your rotational inertia that you're looking at. So we'll do a back substitution, and immediately this is going to give us the rotational kinetic energy. So here's the linear kinetic energy, here's the rotational kinetic energy. So mass becomes, the mass is the same as inertia. Inertia becomes the rotational inertia. Speed becomes the rotational speed, and that's it. All right, so kinetic energy, linear kinetic energy can be expressed in terms of the rotational kinetic energy. So that's your rotational kinetic energy. It's going to be expressed in terms of joules. And that's it. All right, so let's do a simple exercise. So guys, remember the rotor, you become suspended on the wall. So this little exercise is going to involve a rotor. So we're going to look at the amount of energy required to bring it from rest to that speed. So which means that this thing is accelerating up to 8,250 RPMs from 0 to the speed, right? And somehow the moment of inertia, rotational inertia of the centrifuge is given. All right, so how much energy is required to actually speed it up to that value? So you go from 0 to 8,250 RPMs. All right, so let's do a conversion first to radians per second. All right, the way to do this problem is straightforward. So here's the rotational kinetic energy. How much? Okay, this requires a little bit of an interpretation. So conceptual understanding is crucial in physics. It's not like any other discipline. All right, if you don't have an understanding of what's going on, it's impossible to solve these problems. Some of these problems. All right, how much energy is required to bring it from rest to the speed, which means that how much energy do you have to feed into the system so that it's moving at the speed at some point. So how much energy do you feed into your system? Translated in English means that what is the amount of work it's going to take for you to actually get this thing up to that speed? And you have to remember that the work is a process of transferring energy. So in essence, you're looking at the amount of work that you have to do. All right. So the amount of work that you do is going to go into the kinetic energy of the system, in essence. All right. So there's a formula for that. The amount of work is the same as the amount of energy that you feed into the system. So which means that the kinetic energy of the system is going to change. So that's it. So this represents the amount of energy that you put into the system. So you know the initial speed, you know the final speed, you know the moment of inertia. Initial speed is 0. So you got your terms. So everything is given to you. So you plug the numbers in, and so this represents the amount of work it takes, or amount of energy that you need to transfer to get this thing up to that many RPMs. So it takes about 3 calories of work. You know? All right. So the kinetic energy will split into 2 types. If you have a rolling ball or rotating wheel, rolling wheel, or whatever, it's going to have a translational kinetic energy. This represents the kinetic energy of the center of mass. So you have to follow the center of mass. That center of mass is also the point of rotation. And then it's also going to have a rotational kinetic energy due to the rotation relative to the center of mass. All right, so the total kinetic energy of any system is going to involve the kinetic energy of the center of mass, which is known as the translational kinetic energy. And it's also going to involve a rotational kinetic energy, which is relative to the center of mass. So you have to look at the motion of the center of mass. That's the point that you will have to follow. So there's going to be a linear kinetic energy. And then if there's any sort of rotation, this thing is rotating, there's going to be a rotational kinetic energy relative to the center of mass. All right, so that's going to give you the total kinetic energy. Case in point. So we got this rolling bowling ball. All right, and then let's figure out this total kinetic energy. All right. Its mass is given, the radius is given, converted to meters. We also know how fast it's moving in terms of meters per second. So what's this total kinetic energy? So total kinetic energy is going to involve the kinetic energy of the center of mass. So that's this expression. And then it involves the kinetic energy of the rotational motion relative to the center of mass, the angular motion relative to the center of mass. So kinetic energy of the center of mass is the same expression that we were using, which is 1/2 mv squared. Kinetic energy of the rotational motion relative to the center of mass is going to be this expression. So it's going to be 1/2 rotational inertia, moment of inertia, times the square of the rotational speed. Right, so which means that we will have to add these together. All right, we need to express the rotational speed in terms of the tangential speed. The tangential speed is exactly the it's the speed at the rim of the tire, linear speed at the rim of the tire, which happens to be the same speed as the center of mass. So the tangential speed is going to be the same as the translational speed in essence. So that's what it means, the speed of the center of mass. So the expression for the moment of inertia for the sphere is going to be this. So it's going to be 2 fifths mr squared. All right, so I'm going to express this in terms of that. All right, so I'll do a back substitution now. I just follow that term. All right, so radial distance times the angular speed is going to give you the tangential speed. All right, so I'm doing some cancellations here. So this is going to be our tangential speed. This tangential speed is the same as the translational speed, speed of the center mass. This is not r squared, this should be v squared. I'm going to make that correction shortly. All right, this is happening during the lecture. Obviously, I'm focusing on these terms while rewriting these terms, and I wasn't focusing, so I'm just making the correction. So the tangential speed of the rotating ball is going to be the same as its speed of its center of mass. So we got two like terms, so we can factor that out. Mass is the same, so I'll factor that out as well. All right, the rest is straightforward. This needs to have a common denominator. All right, so multiply this by 5, this by 2, and multiply the bottom by 2 and 5. So it's going to give you 7/10. So this is the kinetic energy, total kinetic energy of the bowling ball. It's not going to be 1/2 mv squared. It's going to be much bigger than that because of the rotational motion. All right, because up until this week, we assumed that kinetic energy was always 1/2 mv squared. That was true for this. If we were just focusing on the center of mass. Now we're also focusing on the motion relative to the center of mass. And all of a sudden, it's giving us a much larger kinetic energy. All right, so this is the problem number 11. This is as far as we got. All right. Now we're looking at test quality questions. So far, everything that we've done is multiple choice quality. This one is a test quality. All right, so we got this long pole. It's going to be balanced vertically on one end. The other end is going to tip over in this direction. All right, so can we figure out the speed of the tip right at this point? It's going to tip over. It's just going to fall. All right, so it's got a length. The length is given. And it's just going to tip over, and we want to know the speed of the tip of this pole at the end of this motion. All right, and we want that speed in terms of mass per hour. So we will assume that the motion is under the influence of gravity, and gravity only. So we will ignore friction, which means that the mechanical energy is going to be conserved. Now, final form of this energy is going to be rotational kinetic energy. The reason why it's rotational kinetic energy is because it's moving relative to the point of rotation. And the point of rotation is not moving, so the point of rotation is right here. It's not moving, so it doesn't have any translational kinetic energy. Right? So the final form of mechanical energy is rotational kinetic energy, and the initial form is going to be gravitational potential. So initially it's here, the final location is here. So final form is rotational kinetic energy, and the initial form is gravitational potential. So gravitational potential energy depends on the initial height, which is going to be L. And that's it. All right, so now let's clean this up. So this is going to be I, omega squared, mg L. All right, so I, we're using it for a pole. All right, so I is going to be, it's balanced at this end, so we will get to use 1/3 ml squared for that. All right, so we'll do a back substitution. All right, and this is gonna be 2 times 3, it's gonna be 6. And we'll get rid of the like terms, m's will cancel. L squared is gonna cancel. And then let's get rid of G, and let's get rid of 6, and then get rid of L. All right, so now get rid of the square. Just wanna get the angular velocity all by itself, and then convert it to linear velocity. All right, so for angular velocity can be expressed in terms of the tangential velocity. So that's what I'm going to do. R is the same as L. So we'll do a back substitution. All right. So keep canceling out the like terms. L and square will cancel. Get rid of L, get L on the right-hand side. Okay. So we're trying to figure out the final speed. So get rid of the square by square root on both sides. All right. So we came up with an expression for the final speed. All right. So it's going to be 6 times GL. It's going to give us the speed at the time of impact. It's about 26 miles per hour. It's about 26 miles per hour. The lecture is getting real intense now. Gotta put your knife. All right, so now let's make the lecture interesting. This seemed like a really meaningless exercise that only a physicist would love, which is probably true. And I don't really like these kind of exercises because I have a tough time finding meaning in these kind of things. I mean, who cares that we were able to figure out the speed at the bottom? All right. Even from a physics perspective, this is a really weak problem. But there's a backstory that's going to make it interesting. All right, so let's focus on the backstory. All right, let me just stop this because you guys have to see this now. All right, so you guys see this knife? All right, so we'll do a small demonstration. I need to get back a little bit so you can see it better. I'm using this knife as an example because I can turn it off. All right, I was going to use a meter stick, but I don't have it. Okay, so basically, we just let it tip sideways, so you're following the tip, and it's going to hit the ground at a certain speed. So that's in essence what you're doing. All right, so you're just following the tip, and you're trying to figure out the speed. Okay, cool. That's it. The example that we did was exactly that. It's like lacks a lot of imagination. It's not an interesting enough problem. If you're a mathematician, you probably drew over it. But for the rest of us, not a big deal. All right. About 15 years ago, I'm visiting a friend of mine, a physicist, in an office building, and she was working as a computer scientist at that place. So his co-worker was an actual computer scientist. So we were discussing physics, and then the co-worker just barges in and says, do you know that the tip of this knife, for example, this is the example that I'm giving, when it's tipping over just like that, its acceleration would be larger than the acceleration due to gravity. All right, so what that means is if I were to drop an object like a small marble from this height, and you know it's going to be accelerating under the influence of gravity at a rate which is 1g, roughly about 3 meters per second squared. So according to this guy, the tip would be accelerating at a rate larger than the 10 meters per second squared. That's what he said. So as soon as he said that, I said, no, absolutely not. It's just like, it's nonsense, all right? Because this tip is still accelerating under the influence of gravity, so which means the tip cannot fall at a rate larger than the gravitational acceleration. Which is absolutely no way, it's not gonna happen. He said, oh, no, the tip is gonna accelerate at a larger rate. Okay, I was slightly ticked off because I'm a physicist and this guy's not, and he's disagreeing with me on something that clearly he does not understand. All right, he's a computer scientist. He probably had to take physics at some level. His understanding of physics is obviously lacking. He doesn't understand that this motion is happening under the influence of gravity, and there's absolutely no way the tip is going to accelerate at a rate larger than gravitational acceleration. So he insisted that it would. I was being real dismissive. I was just going to change the topic, and I don't know. I think because of his attitude or something, I got really ticked off. I said, prove it. All right. So when somebody says prove it in physics, it doesn't mean, hey, conduct an experiment and then let's measure things and then boom, 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 we'll figure it out. No, when we say prove it, which means that get it. Paper and pen or pencil, just show me a derivation. Just work it out. Just work it out. That's how we do it. Just like the way I've done the previous problem. Just work it out. Explain what you're doing. Work it out. Just do it on paper. Let me check to see how this goes. Except there's a slight problem. That approach does not work with this guy because he's not a physicist. He's not a physicist. He's a computer scientist. He said, I can't prove it. But he said, I remember it clearly as if it was yesterday that my physics professor did this on boards. And he proved it to us that the tip is going to accelerate at a rate which is getting larger than the gravitational acceleration. It was just so profoundly the opposite of what he was thinking, because at the time he was thinking just like me that the tip would accelerate at the same rate. And it was just so weird that he still remembered that 30 years later. Okay, so I'm thinking, okay, so this guy evidently thought exactly the same way as I did. And all of a sudden he saw something on the board which was so contrary to what he believed, and he still remembered it. I said, okay, well, that's fine. I said, where'd you go to school? And he said, MIT. And I'm thinking, oh, okay. So, guys, the MIT people are different from the rest of us. Right? These guys are exceptionally gifted. All right. So this guy actually took engineering physics at MIT, and he remembers that little thing from 30 years before. And all of a sudden, I'm thinking, I wonder if there's any validity to what this guy's thinking. Okay. I figured that if his professor was able to do a derivation like that, it would be real easy. I'm also a physicist. I could just do the same derivation. It's not a big deal. Now we'll check to see if this guy is right or wrong. Okay, so that's what we'll do. So that's the backstory. And the reason why this problem becomes interesting for me, because I had to figure this out, because I figured that his professor was able to do it. And being a physicist, I figured that if one person could do it, the other guy could do it as well. I can do the same thing. So that's what we'll do. All right, so what we did by using this problem, we figured out that the tip is going to move at this rate. All right, so here's the speed of the tip. Then we'll turn this into a mind twister. We'll drop an object from the same height and figure out its speed. All right, so it's exactly the same length of this pole. All right, so this is the pole which is going to tip over. So we're going to compare the speed of the tip to the speed of a falling object. So this one is in free fall. Once again, the motion is going to be under the influence of gravity. So mechanical energy is going to be conserved. In free fall, the initial form is going to be all potential energy. Final form is going to be all kinetic energy. All right, so this will be the kinetic energy of the center of mass. That's it. So this is the final form. Final speed is going to be the speed due to free fall. F is going to be the free fall speed. All right, so here's your free fall speed. And here's the speed of the tip coming down because of the rotational motion. So final form of mechanical energy is the rotational kinetic energy. Initial form is the gravitational potential energy. All right, so we've done the work for this one. So instead of repeating this, I'm just going to steal only the solution. So finish up the work. This is what you end up getting. Immediately, you notice something. All right, the speed due to free fall, gravity, is here, and speed due to the rotational motion is here. You know, this is going to be a larger number than this one is. So the tip is moving faster than the freely falling object. All right, so evidently, it was right. What's happening is the tip is accelerating at a rate which is larger than the gravitational acceleration. In fact, this speed is going to be 1.7 times larger, more than 1.5 times larger than this speed is. All right, so the question is why? Why is that true? All right, the answer to that question is straightforward. It's related to this, guys. Everything up to the center of mass, which is the center of balance. Remember, the forces are always applied to the center of gravity. The center of gravity is going to move at a rate which is 1g. All right, so the center of gravity is the portion that moves at a rate which is 1g, roughly about 10 meters per second squared. Anything over the center of gravity, anything up the center of gravity is going to accelerate at a rate equal to gravity. Anything above that point is going to accelerate at a rate larger than the gravitational acceleration, provided that this is a one single solid, well reinforced structure. All right. So up to this point, it's going to be 1g. Anything above this point is going to be larger than 1g. And for the rest of it to be able to fall at a rate larger than 1g, it needs to be properly reinforced. It needs to be properly reinforced. It needs to be properly reinforced, just like this necklace. All right. It's got a center of mass. It's going to be located here somewhere. So you actually balance it relative to the center of mass. So when it's actually falling, because it's properly reinforced along this direction, all right, everything moves as a solid chunk of unit. Up to this point, it's going to accelerate at 1g. Anything above this point is going to be over 1g. Because it's a solid unit, everything's going to get pulled down as a solid unit. So the sections over the center of gravity accelerates at a rate larger than 1g. Except these chimneys are not properly reinforced, so they will offer resistance to change in rotational motion. So they will just break off because they just want to keep falling at a rate of 1g. And all of a sudden, everything makes sense. And everything makes sense out of that little discussion that I had with the guy. And as it so happens, my understanding of physics wasn't good enough to comprehend of what he was trying to say. And obviously he wasn't a physicist, so he thought that he could remember the conclusion of the argument, but he couldn't remember what the argument was. And I had to reconstruct it only to realize that that explains why the chimneys break off at certain points. And every single falling chimney is going to break off at some point because they're not properly reinforced sideways usually. All right, so here's the second mind twister. This one also, this was a learning experience as well. And this happened because I was reading one of the local newspapers. I don't know which town I was in. And there was an article that caught my eye. This is about a bunch of high school students conducting a physics experiment using a car, and they were driving the car onto black ice, and then they would just lock up the brakes, let the car skid, and they were measuring the speed of the car on black ice using a radar. All right, so by using a radar gun, so they're looking at the speed of the car. Car is going at 60, it's on black ice, and then you lock up the brakes, and black ice is going to offer a little bit of resistance. So they were trying to figure out the resistance of black ice. That's what they were trying to do. All right, so they have a radar gun. So using a radar gun, you're watching the speed of the car. So the car hits black ice, hits the black ice at 60 miles per hour. You lock up the brakes. And because the black ice does not offer a lot of friction, the number that they were supposed to see was supposed to go from 60 miles per hour to 59.9 something. All right, 59.8, 59.9 miles per hour. It's going to be a very small but measurable change in speed. So that's what they were supposed to see. Except every time they repeated the experiment, they noticed that there would be a slight increase in speed. The speed would just go up to like 60.12, 60.13 or something. It's a very slight increase in speed. That didn't make sense to anyone. All right, so they couldn't explain it. The teacher was not able to explain it. They didn't know what to do with that information. The measurements were accurate enough, but they were looking for an explanation, and no one was able to come up with an explanation because they thought that this was real bizarre. When I read it, I thought the same. I said, this is bizarre. More than likely, they got something wrong. I was very dismissive of it. Because black ice is going to offer resistance. It's a very small amount of resistance. The speed of the car would change just slightly. I don't know how measurable it is using a radar gun, but there would be a slight change in speed. And the slight change in speed would be in the negative direction, which means that it's going to be less than 60 miles per hour. It's going to be slightly less. It cannot be more, but it can be slightly less. In the absence of friction, the vehicle was moving a straight line at constant speed, so there would be no change in speed. Because there's a little bit of friction, I would expect the speed to be slightly less. And there's absolutely no reason for the car to speed up in the absence of an external force. All right. Friction is an external force, it's opposing motion. So I expect that there would be no speeding up. There would be no acceleration, positive acceleration. So I just completely dismissed it. I read it. I said, oh, this is bizarre. More than likely it's an experimental error of some sort, or the article is completely made up. All right. So I was very dismissive. Anyway, so I'm teaching this course, this very lecture, I don't know, 15, 16 years ago. And all of a sudden I go, oh, all of a sudden I go, of course this makes sense. Of course the car is going to speed up. All right. And this is the sort of stuff that you kind of realize only if you're a teacher. Okay. If you're a student, you won't be able to get it. And if you're doing research, you develop a better insight. But if you're forced to explain stuff to other people, you understand it better. Because if you don't understand it, you can't explain it. And for you to be able to explain it, you have to understand it first. And also, you understand better while you're explaining it. And this is one of those things. The reason why the car is speeding up is because of the fact that the kinetic energy is a composite kinetic energy, which means that it's got two parts to it. You're dealing with the kinetic energy of the center mass of the car. And so you're also dealing with the kinetic energy due to the rotational motion of the tires. So you got two types of kinetic energy. So when the car hits the black ice, what's happening is there's very little amount of friction acting on the car. It's so small that you can kind of ignore the frictional force. So, which means that the change in total kinetic energy of the car is going to be zero. So you don't expect any change in kinetic energy of the car. So it's just exactly the same as inertia. The object is going to maintain its initial motion in essence, but something else happens there. So there's no change in kinetic energy, which means that before you apply the brakes and after you apply the brakes, the total kinetic energy of the car is going to remain the same. So kinetic energy is going to remain the same. Except you have to remember that the kinetic energy is a combination of translational kinetic energy, which happens to be the kinetic energy of the center of mass. And then you also have the rotational kinetic energy, which is the kinetic energy relative to the center of mass. All right, so if you lock up the brakes, what's going to happen is the rotational kinetic energy is going to go down and the translational kinetic energy is going to go up. So which means that the rotational kinetic energy is going to get transformed into the translational kinetic energy, which means that the center of mass is going to speed up, which means that the car is going to speed up just slightly. That's what it means. And that's exactly what these people were measuring. I've done the computations on this one, and sure enough, I came up with a number which is slightly larger than 60 miles per hour. All right, so the total kinetic energy remains constant. For a given constant kinetic energy, when you lock up the brakes, obviously the rotational kinetic energy goes down, and the translational kinetic energy goes up by the same amount. All right, so let's get back to the Galileo's famous incline experiment. All right, so will these roll and reach the bottom at the same time? All right, so you got a solid cylinder and you got a rim. All right, so once again, Galileo is trying to figure out the acceleration due to gravity. And his underlying assumption is that if everything falls at the same rate, does this mean that everything will also roll at the same rate so that you can figure out the acceleration due to gravity? All right, so this is a standard physics problem. This is a standard physics problem. Is that a copy in it?
Yeah, it wasn't hot.
Oh, okay. This is a standard physics problem, so this is the one that you guys may have to exercise. All right, so let's have two rolling cylinders. One is going to be solid. The other one is going to be hollow. All right, so this one is a solid cylinder, this one is a hollow cylinder. And let's roll them down. So which one is going to reach the bottom first? All right, so here's the initial height. Ignoring friction, gravity is only for a second, so which means that the mechanical energy will be constant. Initial mechanical energy is the same as the final mechanical energy. Initial mechanical energy is a combination of kinetic and potential energies. And kinetic energy is a combination of translational as well as the rotational kinetic energy. So translational and the rotational kinetic energy. Potential energy is the gravitational potential energy. It depends on the height, so the initial height. All right, so let's write out the formula. All right, so translational kinetic energy, rotational kinetic energy, potential energy. These are the final terms. Initial kinetic energy, rotational kinetic energy, and initial height. We will have a bunch of zeros, so it's going to simplify the equation. Final height is 0. Initial speed is 0. Initial rotational speed is 0. All right, and then this is the speed of the center of mass. This is the rotational speed. The rotational speed can be expressed in terms of the tangential speed, which is the same as the translational speed in this case. So rotational speed is going to be expressed in terms of the tangential speed. So we'll do a back substitution. All right, so we will factor out the like terms. So 1/2 is common, b squared is common. So let's just factor out the like term. All right, so let's isolate the final speed. So I'll get rid of 2, get rid of the expression inside the parentheses, and then get rid of the square by taking the square. All right, so we came up with a generalized expression. All right, so a generalized expression goes like that. If you want to know the speed of an object, obviously it's going to be inversely related to the moment of inertia, which is the rotational inertia. And rotational inertia depends on the geometry. That's it. So the one with a larger moment of inertia is going to move slower. So objects with different geometries are not going to move at the same speed necessarily. And what's going to happen is the moment of inertia, the rotational inertia is going to matter. The ones with larger moments of inertia will move slower. The ones with smaller moments of inertia will move faster. So let's do a case study. So you got a hollow cylinder, which is a rim. So it's got a moment of inertia, mr squared. So let's substitute this back into that formula. All right, so r squares will cancel. And we have mass plus mass, so it's going to be 2m. 2's will cancel, the masses will cancel. So the mass is not going to matter. The only thing that's going to matter is the height in terms of how fast the rim is going to move at the bottom. Then we have a solid cylinder, which is going to have a moment of inertia, which is half of the rim. All right, so r squares will cancel. All right, so we need to have a common denominator now. So multiply and divide this by 2. And then add them together. So masses will cancel. Denominator of a denominator is a numerator, so it's going to be 4/3 of GHZ. So solid cylinder is going to have a larger speed than the hollow cylinder. Yeah. All right, so evidently the mass is not going to matter, and the radius is not going to matter, but the geometry will. All right.
We're going to look at a couple more demonstrations of rotational inertia. Now, to review, rotational inertia is the property of an object that deals with a resistance to a change in its state of rotational motion. We know that this depends upon the mass of the object and the way that mass is distributed from the axis of rotation. For the first demonstration, let's look at this aluminum disc. This has quite a bit of inertia because much of the mass is distributed far from the axis of rotation. We're going to put this in motion with the motor and let it spin while we're doing something else. And it will take some time to spin down because of its large inertia or rotational inertia. So I'll get this thing going. I'll let it spin up here for about 5 to 10 seconds. And I turned the motor off now, and now it's just slowing down. Now, it will slow down because there's frictions in the bearings, but it's going to take a while to do that because of its large rotational inertia. While that's happening, let's take a look at this demonstration right here. Here I've got 2 discs which have the same radii. One of them is an aluminum ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disc. What we're going to have them do is race down this incline. And the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is 0. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is. So the wooden disc rotated more quickly and won the race down the incline. That makes sense because we said that the metal ring had greater rotational inertia, so there's a greater resistance to a change in its state of motion. It's going to have a smaller rotational acceleration as it goes down the plane. Let's take a look now at our disc. You can see that it's still turning. It's slowing down. It's almost stopped by now. But if we could make the friction in the bearings much, much less, this could continue spinning for a long period of time. If we made this a very large metallic disc, we could store a large amount of energy, rotational energy, in that disc, and we could keep that energy stored for a long period of time. Such devices are called flywheels, and they are used exactly for that purpose, for energy storage. To a change in the state of rotational motion. We know that this depends upon the mass of the object and the way that.
This guy did a really good job in explaining it, but let's just go over it one more time.
The number 979-848-2161.
Okay, so you got two cylindrical masses. One of them is solid, the other one is hollow. So which one is going to reach the ground sooner? Which one is going to reach the bottom sooner? Well, got a really good prediction out of it first. We know that this one is going to reach the bottom soon. All right, so the solid cylinder is the one that's going to reach the bottom soon. All right, because it's got a rotational inertia, which is going to be smaller than the hollow one. All right, so you got this rim, and then you got a solid cylinder. So solid cylinder is going to move much faster because it's got a smaller moment of inertia. Moment of inertia means the tendency to retain initial rotational motion or resistance to change in rotational motion. All right, so the question is, if both of them have the same mass, why then does this have a smaller moment of inertia? All right, and then he provided a really good explanation for it. He said this one that you're looking at, it's all of its mass is concentrated at a radial distance r from the point of rotation. So point of rotation is going to be in the middle. Center mass is going to be in the middle. Here, the mass is uniformly distributed away from the center. So closer to the center, obviously the moment of inertia is going to be smaller for the mass distribution. As the mass distribution starts to move away, as you start to move away from the center, the mass distribution is also going to be uniformly distributed all over the place. All right, so here the mass is going to be concentrated. All the mass is going to be concentrated at a radial distance of r away from it. Here, the mass is going to be uniformly distributed into the region that you're looking at. As a result, what happens is this is going to have a moment of inertia, which is going to be smaller than this one is, in essence. Okay, if you want to know why it's 1/2, well, it comes out of the mathematics. Okay, it's beyond the scope of this course. For that sort of stuff, you have to take engineering physics. All right, so conceptually, you just need to understand that the mass is uniformly distributed all over the volume of this mass that you're looking at, the cylinder that you're looking at. Here, all the mass is going to be distributed at a radial distance r away from the point of rotation. As a result, this is going to have a much larger moment of inertia, and as a result, that one is going to have a much smaller moment of inertia. All right, so the one with the larger moment of inertia is not going to speed up as fast because it's got a lot of resistance to change in motion. And the one with the smaller moment of inertia is going to speed up much faster because it's not going to offer as much resistance to change in rotational motion. So the solid cylinder is going to reach the bottom sooner as a result. Ooh, all right. All right, so we can test that at school, actually. That's weird. That means all spheres should be moving at the same speed. All right, so let's finish this up. Let me just check something real fast. All right, so what do we have? So moment of inertia is going to be directly proportional to the square of the radius. it's going to be directly proportional to the mass for a given size. All right, so a baseball bat is going to be easier to swing from the more massive end. All right, so this end is going to be less massive. This is more massive. The reason why that is so, because the smaller the mass that you're trying to swing, the smaller the moment of inertia is. So, which means that's going to offer smaller resistance to change in motion, rotational motion. Rotational kinetic energy is related for a given moment of inertia. It's going to depend on the square of the rotational speed. So, which one will have a greater acceleration rolling down an incline? Is it the bowling ball or the volleyball? All right, so the bowling ball is going to have a greater acceleration because it's got a smaller moment of inertia than a volleyball. The reason is because the mass is uniformly distributed in that case.